Good afternoon, students. So in today the digital signal processing class, we are going to continue the previous concepts. We do have discussed in the previous class the finite word length. So basically, what is a finite word length? Finite word length describes the two concepts. One is the truncation, second is the rounding off, right? So what is the meaning of truncation? If you do have an infinite number of samples that you want to make it into finite number of samples, we use a concept called truncation, right? So while we are doing these kind of things, we are getting three types of errors, right? One is the input quantization errors. Second is product quantization error. Next is coefficient quantization errors. So basically, what is the meaning of quantizations? So to do any kind of signals into the processing in digital form, we get two things. One is the quantization. Second is the sampling, right? So for this particular thing, we'll give the signal x of t. So it will convert into x of nts, right? That made by the sampling theorems. What is sampling theorems? Whatever the signal fs should be greater than or equals to 2 times of maximum frequency. That means it is going to convert the signal into the number of samples. So this is what the concepts when we are considering for converting the signals in order to get the signals in terms of I of n, right? So to do these things, we do have the quantizations and the samplings. So quantizations and samplings we are getting in finite word length when we talk about the digital signal processing, right? So for doing this particular part, we are going for these three concepts. So what is this input quantization errors and how it is going to eliminate? Input means what? We are giving the input values to the digital signal processor. So when it is taking the inputs, it gets quantized, means the signal, continuous signal is going to convert into discrete form. So that when you are going to convert into discrete form, you get errors. So that errors we are considering to be the input quantizations errors. So when we want to multiply any two bits, the errors what we are getting, those are considered to be the product. Product means what? When you are multiplying the two things, when you multiply any bits a and b, when you want to multiply, when you get the product a into b, the errors what we are getting, so those are called product quantization errors. This will be arises when we get the output of multiplier a and b bit is there. When we have to multiply these two bits, when we want to round off these particular bits, when you want to multiply, we are getting the errors called product error. If you had a bit and b bit, if you want to multiply, if you want to find the product of these two bits, you want to round off these bits. Means what? You want to multiply these bits and you need to write the round off value for it. So if you may have a bit like this, so 1.011, right? You have b bit like this, 1101.11. So when I want to multiply these two, when I want to find out the product of this, the errors what we get is product quantization errors. If you are not able to put the decimal in a proper positions, you may get some errors because decimal values needs to be tallied in a proper form. So for overcoming or the things which we get it inside it, the errors which we get it, it's called it as product quantizations errors. Next is coefficient quantizations errors. So to get the coefficient quantization errors, we are saying that we had the filters, right? So IIR filter, FIR filters. When you want to design the filters, you get a desired output response for that particular filters. So the filter coefficients are computed to find infinite precisions for theory. If they are quantized, the frequency response of resulting filter may differ from desired response. And sometimes the filters may fail to meet the desired specifications. If the poles of the desired filters are close to the unit circle, then the filter which we are quantizing may get the quantization lie outside the circle, leading to instability. That particular part is considered to be the coefficients. The whole thing, whatever theory I read out just now, is what they are saying. If you had a circle, right, we want to find out the region of conversion of that particular circle. If it is getting, like if you multiply this particular thing, you may get the response, right? H of that is equals to summation n is equals to 1 to infinity ai of z power minus 1 plus summation n is equals to minus infinity to infinity. You can consider it both the sided bk. This is ak z power minus k, right? This is what IIR filter response. When you want to find the region of conversion for this z factor, if it is lying inside the circle, this unity circle that is equals to 1, then it is stable. But if you're not getting, you are getting the outside. Suppose you are getting at this region. I'll draw here. That is not visible. I'll write the formula here. H of z, what I wrote here? Summation n is equals to minus infinity to infinity ak z power minus k by 1 plus. This is we did already by using IR filter response, right? So these coefficients, when you want to find the response, if you had a circle, region of conversion, ROC, for that particular circle, if it is not lying inside this circle, if this is not there inside this particular circle, if it is lying this outside, this part, if it is lying outside this circle, then it is unstable you can consider. So when you want to make into stability, you will arise the coefficients, right? So those AK, BK are the coefficients. So in order to get into this stability form, into bonded input, bonded output form, we get the errors in the coefficients. Those are called coefficient quantization errors. Okay, so this is the three errors we get when we want to convert into infinite number of samples into the finite number of samples. We will get the finite word length, right? So that can be done by using quantization and rounding off. So you may get these types of errors. The next concept we do have is, the last concept we do have is types of number systems. So how many type number systems? You already know about the number systems. Binary numbers we had, octal is there, hexadecimal is there, decimal is there. There are different number systems, right? Those are for binary form, digits form. But if the digits are not in the zeros and ones, they are in fractions. Fraction in the sense that the one which we wrote here. See, 1.011, that is a fraction. Because we had point, after that the decimals are there. If you want to write in the P by Q form, the numbers we can be tallied or it can be just put into decimal or fractions. Those numbers are not ideal one, right? So we need to get the output of that also, because that digits also need to be converted into binary form, because our system is digital signal, right? Digitals means zeros and ones only. So when you are converting that kind of fraction into digital form, there are two types of number systems are there. For what kind of numbers I am saying? I am saying the numbers like 1 by 3, 1 by 4. So 1 by 3 is 0.33, 1 by 4 is what? 0.25. These are what? These are fractions. So our system is what? In digital form. That means zeros and ones. So when you had these kind of number systems, the number presentation of that particular numbers can be done in two categories. One is fixed point presentation and floating point presentation. So what is a fixed and floating? That depends upon the kind of fractions which we are considering. So, okay, so when you want to see that particular fractions, when you want to write that fractions, how do we get it? So that getting point and how do we represent it, that is going to be deal here. So see here, so when we are saying the fixed point and floating point presentation, so in that the first category is what? Depends upon the presentation, how the number is going to present. So here in fixed point presentation, it is again classified into three categories. Three types or three categories again, right? So the first is called sine magnitude form, where sine means what? It can be a positive sign, plus sign, or it can be a negative sign, minus sign. So the bits may be, if it is negative sign, it is 2 power b minus 1. That means what is 2 power b? That resemble the class. If 2 power 2, 2 power 3, 2 power 4, depends upon that particular thing, the number of combination of input would be taken. Like in octal form, hexadecimal form, binary form, we will write. So that bits needs to be in sine magnitude form. So we want to take the magnitude of that particular sine bit and will categorize into fixed point. Likewise, we had ones complement. What is the ones complement means? Ones complement, suppose you had bit 1 0 1 1 1. You want to write ones complement means zeros will be converted into 1, ones will be converted into zeros. So what is the ones complement of 1? 0. 0 will become 1, 0 0 0. So this is come under ones complement. That is the second category of fixed point presentation of number. Likewise, we had 2's complement. What is 2's complement means? 1's complement plus 1. If you are finding 1's complement, if you are adding the plus 1 to it, that's become 2's complement. So there are three categories in fixed point presentation. Okay, so these are the three categories. We are categorizing into three forms. So those are these three forms: sine magnitude, 1's complement, and 2's complement. That is there for number presentation, right? Similarly, floating point. Floating point, how do we represent the floating point? So floating point f is equals to 2 power c into m. What is this m is called? M is considered here, it is called it as mantissa. What is this mantissa is? It's a fraction. So fraction value is what? What is the mantissa value? 1 by 2 or 1 means it should be lying between 0.5 into m less than or equals to 1 means whatever the fraction we are considering, that fraction should be in the form of 1 by 2. Whatever the values we are taking, lower limits needs to be 1 by 2 or higher it would be 1. Based upon these two limits, your floating point presentation of that numbers can be obtained. Likewise, what is this C here? C is called exponent factor because we are taking the power of it. How do we get exponent? Exponent can be positive, exponent can be negative. So here we don't have any further categories. Only floating point has these many factors. And this is useful for designing the hardware. So when you had a numbers in a fraction form, when you want to write that numbers into the numbers like fraction 1.011 like that 0.11 something which we do have a fraction and decimal into it, when you want to pass to that particular form, then this is considered to be the floating point number presentation. So they can ask you to write the difference between fixed point presentation and floating point presentation. In fixed point we had the operation of these data should be very faster because here we are using out of these three categories we convert into one particular form and we'll find out. Whereas the operation quite complex and it is slower because there is a complexity needed. First we need to find mantissa, then we'll substitute, we'll find the exponent, then we'll get the floating point. So in floating point there is one more called block floating point is also there. That is a third category. Okay, mostly you will get fixed point and floating point. So here this faster operation because of the complexity it is what? Quite what I can say, it's what slower as because the operations are required is number of steps is required is more. Whereas this is relatively economical means what? It is somewhat cheaper because when you want to design this kind of operation in the DSP for that particular form it is will be quite easy to get the finite word length done. Whereas here since the hardware is needed, that's what it is become costlier. It is somewhat expensive or costly. And here small dynamic range. Why it will be very small? Because directly we are putting into one numbers, as per that number only you will get the range. Dynamic means which are going to be changed. So here small, whereas in this because of these particular factor n number of data can be done. That's the reason here the dynamic range of the data needs to be somewhat more larger as compared to fixed point. Then here round of n overflow that occurs when you go for addition of bits. When you adding 2 bits at that particular time only you will get the round of errors and overflow occurs. This two will be occurs in fixed point when you go for addition. Here we can go for multiplication of data or any other data, round offs and overflow will not occur because directly we are finding the values. So because of these two, because of these all the parameters comparisons, the fixed point and floating point has been obtained, and this is used in fixed point is used in mostly in small computers, whereas floating point arithmetics of that particular calculations used in larger and general purpose computers. That means for all kind of computers, whatever the scientific calculators we are using, we are going for floating point. Okay, so this is the way the fixed point and the floating point of number presentation has been done. Then we're done with our concept of finite word length. So go through with this and make a difference of these two categories. Fixed point, arithmetics you can write here and make the points of that. Arithmetic means what? Adding, subtracting, multiplying, modulus, division, all come under the arithmetic operations. Then second category is floating point arithmetics, and make your difference. Okay, that both are the presentation of number systems. Then the finite word length. So they can ask you this question in 5 marks or 7 marks or 2 marks. Okay, you need to be clear about the concepts. So go through these concepts and make the running notes in order to get the clarity of the concepts. Thank you. So just note down these errors, what all I have said orally, write the theory points for it.